Hello everyone, I'm Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. In this July 2025 lecture series, we are going to discuss about sampling theorem in transforms and biomedical signal processing. Shall we start? First of all, uh, why do we need sampling? Actually, we live in an analog world. Here, everything in this physical world is analog signal. Example, sound, light, temperature, pressure, etc. So, we are in need to convert this analog signal into electrical signals for attaining great precision, accuracy, and resolution. Here, transducers plays a vital role. It converts our physical quantities into electrical signals. For example, electromechanical, photonic, electrical, like that. Examples are microphones, speakers, thermocouples, accelerometers. Here, from physical phenomena to engineering quantities, engineering units, what is happening here? See, first one, our input is physical quantities which is fed into a sensor. Sensor output might be voltage or current which is applied to ADC, your analog to digital converter, and ADC gives ADC counts, and finally which is fed into software. It produces engineering units. What is the role of sampling here? See, sampling, which is used to convert our analog signal into discrete values or discrete points. It doesn't give digital values, it just converts analog to discrete. With the help of quantization, we'll easily convert discrete to digital quantities. These digital quantities are used to analyze our input signals, and it produces so many applications which is used in communication and for in biomedical signal processing. It is mainly used in healthcare analytics. See, first one is representing analog signal digitally. First, this is your continuous analog signal which represents f of x, function of x. Here your x-axis is time and y-axis is voltage, continuous voltage, which is mentioned in the time series. And how do we represent it? We can represent it with the help of discrete values as a time series of discrete values. See your output is a continuous signal with discrete time values, which is the output of sampling. What is happening inside the sampling? See, we need discrete values and discrete points for clear identification of signals, and which is mainly used in accuracy prediction, and for clear accurate algorithm and output we need sampling. We have to sample our signals. This is our final output. Then what is happening inside the sampling? Is there any formula for that? Yes, actually, see here, this diagram shows sampling rate too little and too much. If it is too little, we can't reconstruct the signal we care about, and too much means waste computation, energy and resources. Actually, sampling, which is happening when our sampling frequency fs is greater than or equal to 2f max, your input frequency. Here fs greater than or equal to 2f max, that time only sampling is happening. If fs is equal to 2f max, that time it went for Nyquist rate condition. If fs less than 2f max, the condition is aliasing. For perfect sampling, we need fs greater than 2f max. The sampling frequency should be greater than or equal to our frequency, input frequency, twice of maximum of our input frequency. fs greater than or equal to 2f max. See the diagram. Your input signal f of x, f sampled of x with respect to time. Here our Shannon-Nyquist sampling theorem, it gives f sample should be greater than 2f max. Example, humans can process audio signals 20 Hz to 20 kHz, and audio series sampled at 44.1 kilohertz because your f samples should be greater than 2f max. C. With the help of anti-aliasing filters and ADC inputs to ensure that Shannon Nyquist is satisfied, because we need a perfect samples without aliasing effect, because your sample is too low means we cannot reconstruct a particular signal at the output side. See here, aliasing effect, it gives different frequencies are indistinguishable when they are sampled due to aliasing effect. And with the help of anti-aliasing filters, we can easily remove the high frequency components. For example, we use anti-aliasing filter to filter out the excess high frequency components in a frequency band. See, do I really need a filter? Do I really need to filter my input signal? Yes, because sometimes we experience aliasing effects and Nyquist conditions. That time our signal is very low and it cannot produce the exact input signal. Here in electronics they use ADCs. They are good at analog filtering, and it produces maximum amount of digital and discrete samples. C. Choosing the range for ADC, fixer of bits 8-bit ADC, and the range is small means your signal is like this. If your range is high means it produces signals like this. But we have to fix an ideal range for each and every signal, so we'll get a perfect signal at the output side. See, the first one range is too small, second one range is too big, and your ideal range which provides exact output. See here, choosing the granularity. Here resolution is large range means less information per bit is obtained. If large range, it gives large error, a quantization error. With the help of quantization is nothing but a rounding off. It produces perfect digital output. See here, example for converting between voltages, ADC counts and engineering units. See the diagram. Here your NADC is 4095 multiplied with V in minus VR minus, divide by VR plus minus VR minus, and finally it gives the value of V temp minus 0.986 by 0.00355, which converts your voltage into engineering units. And sometimes oversampling, it should be avoided because we need our perfect exact replication of input at the output side. So we need to address our oversampling, Nyquist condition, also anti-aliasing. The ideal range is good. Here the example for oversampling, 1-bit ADC, right, or noise and dithering count. Dithering, see here, uniformly distributed and upper edge of the box. Here N1 ADC count, it counts 1 over the sampling window, and 0 as 32, it counts zeros over the sampling window. Okay, dithering, sometimes quantization errors can result in large scale patterns that don't accurately describe the analog signal. So we introduce a random white noise to randomize the quantization error. See the output, which is adorable. See the direct samples and dithered samples. See the output. It gives a perfect exact replication of your input at the output side. And so while coming into selection of DAC, digital to analog converter, we have to predefine error, accuracy, resolution, output voltage range, output settling time, and our output coding part. Usually binary coding is adapted here. Thank you. I think you'll get a clear understanding about what is sampling, why do we need sampling, sampling applications, and how to convert an analog signal into digital with the help of electronics. Thank you. Thank you all.